In this example, we're told we have 5 kilograms of water in a piston cylinder assembly, so let's sketch that out. Here's our cylinder, our piston, and we have some water in here. The water is going to be our system, so we'll put a dashed line around that. We're also told the mass is 5 kilograms. And it's initially at a pressure of 5 bar and 240 degrees C. So let's write state 1 has P1 equal to 5 bar absolute. T1 is 240 degrees C. So we know the properties at state 1. The water is slowly heated at a constant pressure, so constant pressure is going to be important. And it's being heated, so I'll just sketch that into my energy flow diagram. If the heat transfer into the water for the process is 2,960 kilojoules, so let me just jot that down. Determine the temperature at the final state in degrees Celsius and the work done by the water on the piston. And we can neglect kinetic and potential energy effects. So let's draw here the work done by the water on the piston in our energy flow diagram. And then for state 2, we know the pressure remains constant, so P2 is 5 bar. Okay, let's get started here. We know, well, first of all, I'm going to try to calculate the work done by the water on the piston. I know that that work is going to be PDV work because we're looking at the work that the water is doing on this piston, so that would be PDV work. So let's write that down. The work done by the system is the integral. So we go from some initial volume to the final volume of P times dV. We know the pressure is a constant, right? We're told in the problem statement it's a constant pressure process, so that means we can pull that outside the integral, and we'll just be left with the pressure times the change in volume. And rather than do just the volume by itself, I'm going to do it in terms of specific volume. And the reason I'm going to do it in terms of specific volume is because I'm given the mass. I can find the specific volume at state 1 just because I know the pressure and temperature, so that means I can find the other properties at state 1. I still have to find it for state 2, but we'll come back to that. So let me just rewrite this as pressure times the mass times specific volume 2 minus specific volume 1. So I'm going to need to determine what those specific volumes are. So let's find the specific volume first at state 1. Okay, so I know the pressure and the temperature. I'm going to go to the saturated liquid vapor mixture table for water organized based on pressure, since I'm given 5 bar here. So let me go do that. So I've got the table here, saturated liquid vapor mixture table for water organized based on pressure. Here we are at 5 bar, and we're told that the temperature is 240 degrees C, but you can see the saturation temperature is 151 degrees C, so our temperature is higher than this, which means that we're going to be in a superheated vapor phase rather than being in a saturated liquid vapor mixture. So with that in mind, I'm going to go to the superheated vapor table for water at 5 bar. I'm going to look for 240 on here, right there. And then I can get my specific volume and other properties there as well. Okay, so let's go ahead and write those down up at the top. So I know let me make some space here first. So I know from the superheated vapor table that V1 is 0.46467 cubic meters per kilogram. Specific internal energy 2707.9 kilojoules per kilogram, and specific enthalpy is 2940.2 kilojoules per kilogram. These all come from the superheated vapor table. And the reason I wrote down these other properties is because they might be useful for us in determining what state 2 is. It's just, I was looking at them at the table, in the table, I might as well just include them. These typically show up when you're dealing with first law analyses. Okay. So now I know what's happening at state 1. I need to figure out what's happening at state 2 in order to get the specific volume at state 2. Now, all I have right now for state 2 is the pressure. I need some other information at state 2 to figure out what all my properties are. So the connection I have between state 1 and state 2 is that we have some heat transfer occurring in this process. And so, it makes me think that we're going to need to do a first law analysis, right? Because in going from state 1 to state 2, we have this expansion going on, there's some heat transfer going on, some work happening. So there's probably going to be a first law component to this. So let me write out the first law. So the change in total energy of the system is equal to the heat into the system minus the work done by the system. The change in the total energy of the system is going to be the change in the internal energy plus the change in the kinetic energy plus the change in potential energy. But we know from the problem statement that we can neglect changes in kinetic energy and changes in potential energy. This piston cylinder system is not moving around, so the speed's not changing, so the kinetic energy is 0. It's not changing elevation, so the change in potential energy would be 0. And then one last thing, the change in the internal energy, I can write in terms of the mass times the change in the specific internal energy. So we have that. The other thing I can do is I can make use of the work done by the system that we just derived over here. So let me write that out. I'll just expand it. Okay, so we have that. So let me clean that up. So we have the mass times the change in specific internal energy is equal to the Q into minus pressure times the mass. Let me rearrange that one. Let me put the mass out front. Mass times the pressure times V2 minus V1. All right, and then I'll just do a little bit of rearranging here just to put terms on the same side. So here we'll have the mass times, we have a U2. Let me make sure I'm getting my signs correct. Yeah, U2 plus PV2 minus a U1 plus PV1. There, I think I have all my signs correct. So when the U2 comes over to the right-hand side, it's a negative. I've got the negative PV2, which would be right here. And then I've got the U1 when it comes over, it'll be a positive, so I have a negative, negative, that makes it a positive. And then finally I have the negative times negative for the PV1, so that one should be a negative. There, I'm glad I checked my signs. Okay, now when I look at that, I'll see that I've got this U2 plus PV2. That's just the specific enthalpy at 2. Similarly, the minus U1 minus PV1, that's going to be equal to a minus H1. It's the specific enthalpy at 1. So I can now rearrange this equation, right? 0 is equal to Qn2 minus H2 plus H1, where these are the specific enthalpies. And so if I look at that for a moment, I know there's the Q into, that was given in the problem statement. H1 I found from the superheated vapor tables, so I have that value. So I can now solve for H2, and that would be my second property over at state 2, and I can then determine the other properties there. So let's just rearrange this. Oh, and there should be a mass in there as well. I neglected to include the mass. Okay, so let me rearrange this to solve for H2. H2 will be H1 plus Q into divided by the mass. All right, so I know H1, I know Q, I know the mass, so I can solve for H2, and that comes out to be 32.2 kilojoules per kilogram. So that's my additional property at state 2. Okay, so now that I have the pressure and specific enthalpy there, let me go back to my thermodynamic property tables for water and just see where I stand on that. So let's remember these numbers, 5 bar, 35, 32.2. So let me go first to this saturated liquid vapor mixture table, 5 bar. Let me just, as a note, write down that H2 is 35, 32.2 kilojoules per kilogram. If I look at that for a moment here, clearly my specific enthalpy is larger than the saturated liquid specific enthalpy, and it's also larger than the saturated vapor specific enthalpy. So that must mean that I'm in a superheated vapor phase again. So then let me go to my superheated vapor table right here, and again I'm at pressure of 5 bar. Let me go through the enthalpies and see where 35, 32 falls in. So if I look at that, it's between those two values. So I'm going to have to do interpolation. So I know my temperature is somewhere between 500 and 600 degrees C. So if you go through the interpolation, I won't go through that here, but if you do the interpolation, you'll get that T2 comes out to be 522 degrees C when you do the interpolation. And since I'm at it, let me go ahead and interpolate to find what the specific volume is. And if you do that, that comes out to be 0.7313 cubic meters per kilogram. Okay, so again, just to refresh your memory on how we did this, what we did is we made use of the first law, expanded out the total energy, really it's just internal energy. We expanded out the work, making use of our PDV work. We recognize that we have internal energy in P delta V, so that looks like specific enthalpies, which we then made use of to rearrange to solve for the enthalpy at state 2. Once we had that, we now have two properties at state 2, so we went back to the tables and we discovered that we're in a superheated vapor phase. So both of these are superheated vapors. And then we've used the tables to find the specific volume at state 2. That was the 0.7313 cubic meters per kilogram. And the temperature at 2 was 522 degrees C. By the way, temperature at the final state was one of the things we were asked to find, so we'll box that in. And we're asked to find the work done by the water. Well, now that I have the specific volume at state 2, specific volume at state 1, and we know the pressures, I can now go ahead and evaluate the work. And if you do that, we get the work comes out to be 667 kilojoules per, well, I think it should be per kilogram. I've got it written down incorrectly in my notes. So it might be kilojoules or kilojoules per kilogram. So let me do a quick calculation just to verify. I'm going to just take a moment here. Apologize for the typing that you're hearing, but it's just me just double checking the numbers just to make sure I have everything right. I'm using Excel to do the calculation. One thing you have to be careful of is you have to make sure you convert the bars into pascals when you do the calculation. Okay, so it is kilojoules. All right, so that's the work done by the water. And then the last thing that we'll do, we're not specifically asked for this, but let's go ahead and plot this on a PV and a TV plot just to be complete. So over here we'll do the PV plot. Here's our vapor dome. Let me draw we're dealing with a constant pressure, so the pressure was 5 bar. And we know that we're in a superheated vapor phase. So let me draw the isotherm corresponding to T1 first. So that was at 240 degrees C. So that'll look something like this. So there's our state 1. This is T1 is 240 degrees C. And T2 was 522 degrees C, so that's a higher temperature, so that isotherm will be above the first one. That's 522 degrees C, so our state 2 is there. And it's a constant pressure process, so we just move along horizontally from left to right. And then, of course, these are the specific volumes, V1 and V2. So you can see that specific volume for 2 should be larger than the specific volume for 1, which is indeed the case. There's V2, here's V1. And if we want to sketch it on a TV plot, let's do that. Again, here's our vapor dome. We're dealing, T1 is down here at 240 degrees C. And let me just go ahead and draw the isobar for that one. And remember, we're still in a superheated vapor phase. So here's our isobar for 5 bars. And so there's our state 1. And then we just move along the same isobar to get to state 2. And state 2 was the 522 degrees C. And we're just moving on the same isobar up to same state 2. So that's what it looks like on a TV diagram. Okay? All right, I think we'll just end the example there then.